to detect and to send the signals through the nerve wires to the brains. For instance, the object is this one. What can be happen? Have a look. So the object has 2 points, A and B, and now we go to project these A and B points behind the lens, following the geometrical properties of the lens. So this line, this star, is going in parallel with the optical axis and behind the lens crosses the focus. This star is going directly without any refractions. So the crossing point is here, means the image of the point A is here. This is the image of the point A. Now the image of the point B is here. The image of the entire object AB is this one. However, have a look. The cells are located just here. So this means that the cells are able to detect only the B point. They are not able to detect the A point because they are not here. The cells are not here. What to do? Please, your solution. This needs an engineering solution. What to do, please? Lūdzu, jūsu versijas, ko vajag darīt?
Varbūt pārvietot, tā rotēt to pašu, to šūnu vietu, tā kā nevis pārvietot, bet rotēt ap savu asi.
So the idea is to provide rotation to the cell plane. So the cell plane to be moved. So for instance, this direction and after this direction. Is it right?
Nu, tas tā kā es tā kā domāju, bet tā
Nē, nu,
jā, bet nu tā kā par punktu ņemt, piemēram, to punktu, kur B ir, un tad ap to rotēt. Jo tad sanāk,
nē, nu, ideja it kā ir pareiza, jā, bet kāds varētu būt inženieri risinājums?
Tieši risinājums, jā, tā.
Jā. Nu, kā es domāju? So, some more ideas?
Ir vajadzīga lēca.
We have one lens already. No any more lenses. But what do we say if the plane of the cells has such a shape? Is it clear? Yeah. So this is the shape of the plane of the cells. The cells are located. So actually, this surface must be spherical. Is the idea clear?
Bet tā ir tā kā izkliedētāja lāca domāta vai...
Nē. Tad skatieties, vat šeit ir tas sfēra, tas retina layers, ja? Tad vat šeit šūnos atrodas, ja? Un tad viņi atrodas uz sfēriskas virsmas. Un pateicoties tam, mēs redzam gan B punktu, kas ir kaut kur šeit taisnīgi, ja? Un A punktu, kas ir it kā nobīdas, tad viņš jābūt kaut kur šeit varbūt, ja? Es atvainojos, tad it kā jābūt šeit, jā, bet viņš īstenībā ir šeit, A punkts. Saprotam?
Jā. Paldies.
Es pamēģināšu vēl vienu skaidrojumu, varbūt būs labāk. Superīgi, pareizi. Skaidrs?
Jā.
Jā.
Tā, pamēģināšu kaut ko pieregulēt, lai būtu skaidrāk. Es sanāk šeit izdot tādu iespēju. Okay. So, Tā būs pilnīgi precīzi. Tagad mēs redzam, kur ir A un B. So now we see A and B locations. Yeah. Okay. Some questions, please.
Nav jautājumu.
So now going ahead. Now the vision defects. With our age, the lens of our eye changes the properties and isn't so elastic as the first years of our life. For instance, some 40, 50 years age, we have the lens that isn't elastic, and that is why the muscles are not able for deformation of the lens. So that is why the lens can't focus the motion or movement of the object from the eye to the closer to the eye. So we see, for instance, that the long distance is very perfectly, but we are unable to see the object at the short distances. So this is so-called, this defect is called hyperopia. So let's try to understand with the scheme. So this is the lens, the focuses, the plane where the cells are located. This is the object, and this is the projection of the object on the cell plane. Everything is fine. Now we are going to move the object in the direction of the eye. So the image is here. We are unable to change the focus of the lens because the lens isn't enough elastic, and the muscles that are connected here to the lens are not able, they don't have enough power for deformation of this lens to extend it, to change this focus, and by this way to bring this image back to the cell plane. Is this clear? Vai tas ir skaidrs? Oh.
Yeah.
Oh. We need actually to do something to move this image artificially to the cell plane. Let's go consider what can be done. So this is our object, this is the image of the object, and now we go back from the image of the object to some unreal or fake position of the real object. We assume that this object is somewhere here. For this, we go to design the stars that come back from the image. This is a direct star. And this is a star that comes back from the image to the fake object. So the fake object must be here somewhere. However, we understand that this fake object is some imagination projection of the real object to this plane. In this case, we need to design some lens that is able to project this real object to this fake one. Is the idea clear? Vai tas ir skaidrs? Lūdzu, jautājiet. Vai ir skaidrs? Lūdzu, apstiprināt, ja ir skaidrs.
Jā, ir skaidrs. Jā.
So let's go to do. So this is the first star that comes here. This is a straight star like this one. No any refractions. So this means that if we go to use some lens, this direct star without the refractions must go to the focus. Must go to the lens, to the center of the lens that we go to use. Now we know the location of this cell, of this lens, I'm sorry. So next, from this lens, we go to build this fake object. So have a look, this is a real object, this is a star that is in parallel with the optical axis. Optical axis of this lens and this lens is still the same. If it is in parallel, so this means must be refracted, this one, when it goes through the lens, like this one. Let's do this. This is a refraction, but the refraction in the direction of the fake image. If you go to prolong it, where is the focus? So this is the focus of this lens. And really, we have the refraction, yes, and from this one, we have the fake image. Is the idea clear?
Yeah.
Yeah.
Let us go to repeat a little bit. So we have the image, we have the object, we have the lens. Now we go to build the fake object, the fake image, the fake object, I'm sorry. So we have it. This fake object is projected to the retinal layer, to the cell plane. We have the image. So definitely this lens must be arranged very individually to each patient, independent on the properties on this lens, on the natural one. So we know the optical axis. We need to locate the spectacular, the glasses, the lens of the glasses exactly at the optical axis of the natural lens. We need to know this distance. We know, actually, anatomically, we know. So that is why we can arrange this lens. Means the focus, to select the focus if you know all of the distances. And next, we can say, we can say actually how effective is this lens for the objects that are here. And typically, for the fake object. And typically, so this distance, this one, is approximately 30, 50 centimeters for reading. We are reading at the distance 30 centimeters. We are watching at the display at the distance maybe 40, 50 centimeters. So that is why these lenses, these glasses, we are using for reading mainly, for working with the displays, with the monitors, and we don't use them when we are walking because we see at the long distances very well without the spectaculars. Is this clear? Some questions, please. Hello?
You're scared.
Okay. Now, the next defect, myopia. In this case, we perfectly see the object at the short distances. However, we have the problems to see the object when it is moved at the longer distances. So if the object is here, its image is here, we don't see this object again. We don't have the ability for deformation of the cells, of the lens, because the muscles are not able to do this because the lens is already so strong because of our age. So that is why we are forced to do something to compensate this defect. And we're going to do this following the previous example. So actually we need to consider, have a look, we are coming back. At the beginning of our talk, we have moved the object to the longer distances. And now we are saying that we need to bring this object to the shorter distance. So if it is here, the image is delivered. From the previous example, we moved the fake image at the longer distance. Now we need to move the fake distance, the fake image, to the shorter distance. So the fake image is here. It's closer to I. The object is at the longer distance than in the previous example. The length, we had this one. And now we go to change the length to this one. This means the shape of the lens is like this one. Is this clear? We had the spherical lens. Now we have the negatively spherical lens. Is the lens of the design clear?
Yeah.
Okay. So this is our object that will go to project to this lens. This is a straight beam, this one. Oh, this is in parallel. That must go to the focus, like this one. This in parallel is going to through the focus. However, for the negatively spherical lens, this must go, the parallel beam must go to the focus in this way. Oh, we have the fake image here. So this is a crossing point of the parallel beam that refracts going to the focus and the straight beam that doesn't reflect. So the crossing point is here, like here. The refracted beam and the straight beam. The crossing point is here, and for this lens, the crossing point is here. Is this clear, please? Vai tas ir skaidrs, lūdzu, jautājumu?
Ir skaidrs.
So now we are going to build this system. So this is a beam, this one that we have here. This is a fake object. Now we go to project this face object to the lens. Yeah. The beam is going to the focus. The focus is here. Oh. This is a straight beam. This is a fake object that is moved closer. And now this fake object is projected to this lens. This is a refracting beam that goes to the cell plane. And this is the straight one that doesn't have the reflection, it has the image. Is the idea clear? Vai tas ir skaidrs, lūdzu, jautājumu? Hello?
Ir skaidrs.
The next one, chromatic aberration. Aberration means the defect of the image. Means not so bright image, not so sharp image, not so clear colors, a little bit spreaded image. So now we speak about the chromatic aberration that is connected with different colors of the white beam, of the white light. So this is a prism. This is a Newton experiment 300 years ago. He worked with prisms and he considered and actually explored that the white beam, this is a white, may be distributed or is distributed into the rainbow colors behind the prism. Because And the reason is very simple. In those times, I believe that Newton didn't know about this. And but the reason is very simple, because each color has a specific propagation velocity in the material. So now we have definitely the colored object. For instance, it has the red color, and the focus of the red color is here. And so definitely we have the image. It's very simple. If you have the blue color, the focus of the blue color must be also, I'm sorry, if the focus of the blue color is at the same place, the image is here. So this means that the cells that are located here, they don't feel this image, they are not able to detect this image. What we need to do, we need to change this blue focus. How? Please, your solution? Lūdzu, ko darīt?
Jāliek nesfēriskā lāca.
Kas lūdzu?
Jālieto nesfēriskā lāca.
Es nesaprotu. Kas lēcu? Vēlreiz lūdzu.
Nevis sfēriskā, bet tā otra lāca.
Otra lēca?
Jā.
Mums tāda ir. Mums ir tikai viena lēca. Kuri mums vajag mainīt fokusu, pareizi? Vai mēs varam to darīt? Allo. Can you change the
mēs
focus?
varam
Ar papildus
izmantot
lēcu varam.
lēci.
Kā lūdzu? Vēlreiz lūdzu?
Ar papildus lēcu mēs varam mainīt fokusu.
Bet papildus lēcas mums nav. Mums ir tikai viena lēca. Nu, tā otra stacionāra, viņa neko nedarīja. Viņa ir stacionāra, viņa priekš mūsu galvenais lēcas, ja, ar kuru mēs varam kaut ko darīt. Tātad mums ir tikai vienīga lēca, ar kuru mēs varam kaut ko darīt. Ko mēs varam darīt? Mēs definējam, ka mums jāmaina fokus. Kā mēs varam to darīt?
Deformējot lācu.
Tieši tā. Atcerieties, šeit ir muskuli. So, to change this focus, actually to adopt the focus, to shift the blue focus to the red one, we need to provide deformation of this lens because of the muscles that are connected to this lens. Because of the deformation, we change the focus, and the image is here. From time to time, this process must be delivered non-stop mode. So, non-stop deformation of this lens means non-stop working of these muscles, non-stop movement of this focus, forward and back. Now it is red. Next part of the millisecond, we have the blue one. Again, the green one, etc. So that is why these muscles are working permanently. If we don't have these muscles, we can't see the colored picture. We can see only one color. Is this clear? Vai tas ir skaidrs? Oh.
Yeah.
Okay. So these are the muscles that can help us, and they are helping. They provide non-stop deformation of the lens. And because of this, the focus is moved to deliver the projection of the colored image of the object. So the next one, spherical aberration. So there are several reasons. We go consider just one. Uniform refraction of the lens material. Have a look. For instance, this is the disc that is transparent for light. And we have one beam, and the refraction coefficient may be estimated as a ratio of the sinus alpha and sinus beta. But actually, this is the ratio of the propagation velocities in this material, propagation velocities of light in this material. So now we have the second one that is in parallel to the first, and definitely we have the same refraction coefficient. Now, have a look. We have the lens. The picture is a little bit different. The stars that are in parallel have the same refraction, the same refraction coefficient, definitely. However, because of the perpendicular different directions, the direction of the refracted stars are not in parallel. So the refracted stars are not in parallel. So that is why if we have the spherical object behind the lens, this spherical object may be transformed into the ellipsoidal one. More far from this lens, more ellipse is delivered. And finally, this ellipse may be transformed into the straight line. So that is why we have the defect of vision. And this is the natural defect. And definitely you can predict that at the area of the lens, at the surface of the lens, where it is bent by the highest way, very strong bend of the lens, this defect is very significant. At the areas when the lens isn't so bent, this defect isn't so significant, because at these areas, these beams are in parallel or very close to being parallel. However, at this area, the beams are not in parallel just because of the shape of the lens. Is this clear? Right, it's clear. Oh.
Yeah.
So this is a lens, this is a beam, this is the other beam. All of them must be focused at one point. However, here we've spoken just now, the refraction is more stronger compared with the beams that are at the center of the lens. This means that this area contributes to the defect of the image that we have somewhere here is very important. And in particularly, when the intensity of the light is very strong, we see this defect. We see this defect very well. What must be done? So your solution, what must be done? Lūdzu, ko tad mēs darīsim? Nu, lūdzu, jūsu versijas. Alô? Nu? Nav nekādas versijas, kolēģi. Allo. Es jūs nedzirdu, lūdzu atsaukties. Jūs mani dzirdat?
Varbūt vajag dot stiprāku gaismu.
Mēs tikko teicām, ja gaisma būs stiprākā, tad šie stāri, kas ir, viņi būs stiprāk redzami šeit, kur ir defekts. Ja bija attēla deformācija, ja mēs stiprāk redzēsim. Tad ko vajag darīt? Lūdzu. This is just engineering solution, nothing more. Nu, lūdzu. Nu, davai domāsim loģiski. Ja vat šis stārs, viņš ir ļoti intensīvs, un ar to šeit mēs redzēsim defektu ļoti, ļoti labi, ja? Tad acim redzot, šim stāram intensitāti vajag ko? Palielināt, jeb samazināt? Kā jūs domājat?
Samazināt.
Samazināt. Tātad, bet atstājot šeit stāru, kas ir arī tikpat intensīvs, kā šis, bet viņam te laušana ir vajagā. Un ar to te defekti no tāda stāra būs mazāk redzami. Tātad sanāk, šim stāram vajag samazināt intensitāti. Kā mēs varam to izdarīt? Palūk saulītē nespīstu? Nesanāk.
Jāpiever plakstiņš.
Tas ir?
Nu, tas ir pievērt aci.
Nu, un ko mēs daram? Pareizi? Tā mēs daram. So we need to cut off these intensive beams. And we are doing this. How? What is the instrument? What is the anatomical instrument that gives us the possibility to do this, to close these stars? This is like the diaphragm. I'm sorry, to my mind, you had already anatomy. It's a course, right?
Nē, nav bijis.
Nebija vēl anatomija?
Nē.
Abi dzīves pieredze.
Kaut ko ar lēcu ir jādara. Tad
Bet ar lēci mēs neko nevaram darīt. Tad lēci diafragmas nav. Bet kur ir diafragma?
This is eyelid.
Yeah. So, it's here. This is a diaphragm. This is iris that we change the pin, the hole of this iris. When the light is very bright, we decrease this diameter. Definitely, we decrease the defect of the image, the spherical aberration image that is developed here. So this is the trick that we need the iris. Definitely the iris we need to decrease the intensity of light to don't damage the cells. But this is other story. Tā, kāpēc jums nebija anatomijas? Jūs esat no otrā kursa?
Nē, no pirmā.
Otrajam kursam bija anatomija.
Pirmā kursa jau notiek anatomija, pirmajā semestrī, ja es nemaldos.
Bet mums nav bijis.
Jums nav bijis?
Mums notika otrajam kursam pirmajā semestrī.
Labi, es pierakstīšu un uzskaitīšu. Labi. So the next defect is the astigmatism defect. And now we have the break 5 minutes, and after that we come back to this to consider this defect. So 5 minutes break. So means 9:05 we come together back. 5 minutes, так быть. Tā, turpināsim, jā. Dzirdam? O.
Jā, dzirdam.
So the next, astigmatism. So this means that the image, for instance, the dotted one, is spread. Actually, we can see two dots instead of the one. So this is connected with the asymmetry of the lens. So this is the lens, three coordinate directions, X, Y, and Z. And here you see that the lens really isn't the spherical, this is like the ellipsoid. And so there are two planes. We can divide this lens into two directions, Z and X direction, and actually by two planes. And so we have the meridian, and this one, and the sagittal plane. So this means that we can assume that the lens consists of two lenses. One is this one, and the second one is here. So one and the second. So the green one has the focus F, and in the ideal case, if everything is symmetrical, the object is projected through the F, and so we have the image here. And for this sagittal or sagittal perhaps plane that has the focus here somewhere, we have to have such a image here. So in ideal case, this focus F, the red one, must be the same as the focus green F, and therefore we have the image of the red one at the same plane when we have the green one. However, you see that the lenses, because these two lenses are different, because our length isn't the homogeneous. It has different diameters in two different directions, means different focuses. So we have splitting of the image. So the green one in this direction, so this one is located here, and the red one is located here. I'll change the colors. Okay, it's better. Okay. So, is this clear? No.
Jā, pagaidām ir skaidrs.
So, this is the real situation. So this is a normal vision when the lens is very symmetrical and very homogeneous. So we have the projection on the, So the lens is very homogeneous. We have the projection of the object at the retina layer as one point, one dot. However, in the case of the astigmatism, so the lens isn't symmetrical, and that is why two focal points are delivered, and we have splitting of the dot. We have, instead of one image, we have two images instead of one. So the next defect of astigmatism is connected with inhomogeneous refraction. So everything is geometrically fine, homogeneous, spherical, symmetrical. However, in two different planes, the sagittal and meridian, the refraction indexes, the refraction coefficients of the light are different. So let's go to consider the refraction at this plane, in the digital, and in the meridian. So this is a focus for both planes. Must be the same because everything is spherical. And so now let us go to project this one through the green. So this is the line that goes through the focus, and this is through the center of the lens. So the image is somewhere here. We have the image. Now let us go to project in the other plane. So by the same way, this is in parallel, and this is the beam that crosses the center of the lens. So the image is here. So everything is fine. Because effect of the lens, because of the defect of the lens, I'm sorry, I need to reply to. Так, у меня сейчас занятие, я перезвоню, да. So if you have, for instance, the defect, the inhomogeneous refraction of this lens in this direction and this direction, the refraction is different. So we have different focuses. Have a look. Now the focuses will become splitted because of different refraction coefficients in different directions. Oops, they're splitted somewhere here. Now let's go for the projection, for the imaging. So through this focus, we have this line, and this is the central beam. And now we have the image, and now we go to project this vector. So through the focus, and this is a direct stride, direct beam. So the crossing point is here, and the image is here. Have a look. We have the defect. So again, everything geometrically is spherical. However, the refractions are different in different directions. So that is why we have the vision defect, astigmatism defect that connects with inhomogeneous refraction coefficients of the cells. Is it clear with tas ir skaidrs?
Jā, ir skaidrs.
So now we go to the other aspects of the optics. It's a little bit more difficult. So for instance, we have the object that has the dimension d, for instance, a circle with a diameter d. And this is the diameter of our iris diaphragm, d small. So this is the distance of vision, L, and this is the distance from the lens to the retina layer, somewhere here. Typically, this one is somewhere 30 centimeters. And this one, anatomically, we know 25 millimeters. So this means that this distance is significantly longer than this one. Speaking about the diameter, if it is somewhere 1 centimeter, 10 centimeters, approximately, and this is 1 millimeter, again, anatomically, approximately, maybe 2, maybe 5 millimeters. So, but nevertheless, D capital is significantly larger than the D small. In this case, so-called Fraunhofer diffraction takes place. I believe that you became informed from general physics about Fraunhofer diffractions. Do you know about this? Please reply. Hello? Vai zinām Fraunhofer diffrakciju? Allo.
Nu, būtu labi atgādināt.
Okay, labi. So, Fraunhofer has considered the beams that are going in the parallel ways to the very small diameter diaphragm, to the diaphragm that has very small diameter. So the scheme is like this one. So this is the length. The length is very, very thin. This means no spherical astigmatism. It's very, very ideal. No any other astigmatisms. And the beam is a very monochromatic. So everything is ideal. And this is the screen that we go to project the image of these beams to the screen. How do you think? Is the screen illuminated homogeneously or not? How do you think? What's your feeling? Or nu, mums jautājums ir skaidrs.
Jūs varat lūdzu latviski atkārtot?
Kā lūdzu?
Latviski atkārtot jautājumu.
Ok, tātad, vat šeit ir gaisma, kur ir salikta no stariem. Tie stari ir ļoti paralēli. Ja? Šeit ir diafragma ar caurumiņu. Caurums ir ļoti maziņš. Šeit ir lēca, kas ir ārkārtīgi ideāla. Nekādu defektu tur nav. Viņa ir ļoti plāna. Nekādas tur kromatiskas aberācijas nav, sfēriskas aberācijas nav. Nekas tur nav. Nekāda astigmatisma nav. Viss ir ok. Šeit ir ekrāns. Un tagad šis stārs nāks uz ekrānu. Un tie stāri šeit izgaismos ekrānu, apgaismos. Un tagad mans jautājums ir tāds, kā jūs domājat, vai šis ekrāns būs apgaismots vienmērīgi, homogēni, jeb ne?
Nevienmērīgi.
Kā jūs domājat, kur būs lielāka intensitāte, kur būs mazākā?
Lielāka būs pa vidu un mazākas būs pa galiem.
Ok, tas ir jūsu galīgais lēmums?
Jā. Tas ir mans variants vienkārši.
Jā, es saprotu, jā. Tā, vēl kādas idejas? So the first option to answer my question is very simple. So the highest intensity is here and the low intensity is somewhere at the side, at the periphery. More or less right. However, there are several restrictions. This diameter is very, very small. So these beams are very in parallel. This means that the source of the light is very, very far away. Means the beams are in parallel. This distance is significantly less than the distance from the diaphragm to the light beam. And in this case, the situation is completely different. Have a look. So-called Huygens principle, somewhere from the 18th, 19th century, tells to us that we are able to consider each point within the diaphragm as the source of the light waves. So here, just to simplify the situation, I identify two centers. This is the center and this is the center. And they generate the beams. So they are excited by the external beams. And they generate the beams to transfer these beams here. Actually, they are spherical and the beams are able to go in different directions. But we are interested in the directions that go to the screen. So this is a spherical front, and each dot of this front delivers the beam. So that is the scheme that I'm saying, in any direction the beam is able to go. And actually, this is true following the Huygens principle. Now we go to consider two beams. They are in parallel. Because of the refraction, they must be focused somewhere here, but they have different ways or different runs. This is shorter, and this one is longer. However, we know that the light beam is actually the wave. If this light is very monochromatic, I said this at the beginning, we have the very monochromatic waves here and here. Until the length, they are equal. However, behind the length, they are a little bit different because the runs of them are different. So at this point, these beams come passing the different ways. What can be happening in this case? Please.
Tieši tajā
Jautājums ir-
P punktā.
Kas lūdzu?
Tieši P punktā,
Jā,
kas
tieši pie.
notiek,
Jā.
kur
Kas
notiek
varētu-
interference.
Notiek interference. Tas nozīmē, nu,
Savstarpēji dzēš viens otru.
varētu būt, varētu arī nebūt.
Maksimums veidojās.
Kā lūdzu?
Veidojas maksimums tajā punktā.
Varētu būt maksimums un varētu būt arī minimums.
Tātad vienkārši tā kā viņi iedarbojās abi divi.
Jā, tad sakarā ar to, ka viņi interferē un ceļi ir atšķirīgi, bet tie stāri ir pilnīgi vienādi. Bet ceļi atšķiras, ar to tiem stāriem mainās fāze. Un tad P punktā varētu pienākt stāri ar vienādu amplitūdu uz augšu, ar vienādu pozitīvu amplitūdu, ar to viņi saskaitās. Ja varētu atnākt stāri ar vienu pozitīvu un vienu negatīvu amplitūdu. Viņi saskaitās un rezultāts ir 0. Tas ir skaidrs.
Jā, ir.
So, the beams passing this hole, these pins, very, very specifically following the Huygens idea, the Huygens principle. So we're saying this is a diffraction of these two beams. Here, they interfere between themselves, and as a result, we can meet here the maximum intensity or the minimum intensity. And actually, Fraunhofer analyzed this case and calculated that independence on the diameter of the pin and the angle phi, the intensity at the point P depends like this one. Have a look. The wavelength, the B, and the phi. So we have here the diffraction picture, like this one. Definitely the highest intensity is at the mid, as you said before. The lowest intensity here, however, there are the diffraction maximums. Is this clear? Hello? Hello?
Jā,
Jā.
tagad ir skaidrs.
Okay, so this means that our cells that are located at this plane, they detect the diffraction picture. The image is fragmented because of this diffraction effect, but we don't see this. What is the reason? How do you think? So, idea. Actually, we need to avoid this diffraction influence, we need to make some engineering solution. What can be offered from your side? Vai mans jautājums ir skaidrs? O,
Vai lūdzu vēlreiz uzdot?
ok, labi. Tātad mums šeit ir skaidri redzama difrakcijas bilde. Un Fraunhofer parādīja formulu, pēc kuras mēs varam aprēķināt intensitāti un tiem maksimumiem atkarība no leņķa. Tātad sanāk, ja šeit atrodas šūnas, kas redz gaismu, redz objektu, tātad sanāk, tas šūnas viņi atspoguļo difrakcijas bildi, kas šeit veidojas. Tas nozīmē, ka objekta attēls, kas veidojas šeit, jebkuru detektē šūnas, viņš ir salikts no difrakcijas bildēm. Un tas nozīmē, ka attēlu, kuru mēs redzam, jābūt diezgan, attēlam, kuru mēs redzam, jābūt tāda diezgan raiba bildē. Nu, difrakcijas maksimumi jābūt, bet mēs viņus neredzam. Tad daba ir pietiekuši gudra, ka viņa mums kaut ko tur izdarīja, ka mēs neredzam difrakcijas maksimumus. Un tagad es jautāju jums, ka inženieriem, ko es varētu piedāvāt tiešām, lai izvairīties no tādas difrakcijas efekta, lai mēs viņu neredzētu, lūdzu. Tagad ir skaidrs? O?
Jā, ir skaidrs, bet vajag padomāt.
Nu, protams. Lūdzu. Pardon? I don't hear you clearly. Can you repeat? P changes? Yeah, you mean the diameter of the iris, yeah? Yeah, we can change, for instance, if the diameter of the iris is very, very small, 0. Yeah, we have the infinity of the intensity, so it means we don't have the intensity following this formula, right? Not so good. Yeah, can help. Can help, that's true. But what else?
Mainīt formu šūnām.
Šūnam forma? Bet no šūnas, the idea is to change the shape of the cells. But actually it's the shape of the cell. Es pareizi saprotu, jā?
Ne tieši šūnām, bet to nevis tā kā viņas ir izkārtotas nevis taisni tā kā šajā attēlā, bet tieši tā kā
change the shape of the cell plate, right?
Yeah.
Okay, paskatīsimies. So let's go to have a look what can be happening. So we need to destroy this diffraction picture, but this diffraction picture is developed because of the very well focus of this lens, right? This means that we need to change something to destroy this ideal picture, to destroy this focus of the lens. So we need to move this plane, for instance, somewhere here and here, somewhere here, just to keep the central maximum. We don't need the side maximums. So we have to focus just at one point and to make the shape of the cell plane like the spherical one. And this really will help. Is the idea clear to you? Vai ir skaidrs?
Jā.
Jā,
Again, we come to the idea that the eye must be spherical. You see, at least 3 reasons we know why the eye must be spherical. 4 reasons even. Okay, the questions, please. No questions?
Nav
Nav
jautājumu.
jautājumu.
Nu, nebija tik viegli šodien, jā. Tā. So now we go to continue to the cells. But before this, we need to discuss with you very important question about the exam, because today we have to my mind already the 14th or 15th week. Well, I'm going to check what is the week today. Yes. Yeah, we have the 14th week. So means next Monday we have the 15th week. And plus one more week is the last one for the theoretical lessons. The 16th is the last, and the 17th is planned for the tests, and actually the 18th, 19th typically for the exams. But today, following the COVID situation, we don't have the session time, and we are free to arrange the exam as we want. So that is why we need to discuss the exam date. And from my point of view, I prefer to have the exam before the 12th of June. Is it fine with you?
Es domāju, ka jā.
Tātad pirms 12. jūnijam, ja, organizēt examen. So now, from my point, you have the home task to discuss within your groups the dates of the exam that you prefer, and please consider several options, because you are 3 groups, as I know, and I need to have several options to arrange you by the best way. So each of the group, please deliver to me several options, and we go to negotiate separately with each group, and finally we arrange the exam. Can you do this on Monday? Vai jūs varētu to vienoties līdz pirmdienai? Pirmdienu tā teiks.
Es domāju, ka jā.
Jā, tad jūs man paziņosiet, kaut pieņemsim šodien, rīt, jeb parīt. Jā, pārīt no rīta jūs laikam nepaspēsiet vēl. Tad dienas laika, jā, un es ar jums tad sazināšos, un mēs precizēsim eksāmena laiku. Vai viss ir skaidrs? Foreign students, is it clear to you? You're very quiet today.
Yes, it is clear. Yes.
So on Monday, this is the deadline for you to offer to me the dates of the exams that are mostly preferable for you.
Un
Okay.
drīkst jautāt?
Jā, protams.
Kā vispār eksāmens, kā viņš norisināsies, kāda mums ir tā ideja eksāmenā?
Tad eksāmens ir eksāmens, tā ir tā pārbaudē. Un, protams, ņemot vērā, ka mums viss ir sajaukts šogad, jā. Tad, es teikšu tā, parasti notiek tā, vajag būtu nokārtoti visi praktiskie, visi testi un tikai pēc tam mums eksāmenu. Bet par cik mums viss ir sajaukts šogad, tad mēs varam arī turpināt tādu jaukto procedūru eksāmenam, pieņemsim, kaut kas vēl nav nokārtots, bet var kārtot eksāmenu. Jā, un pēc tam tad saskaitīsim visus punktus kopā. Par cik praktiskie testi un eksāmens nāk viena čupiņā, un mēs rēķinājam vidēju aritmetisku atzīmi. Jā, tā kā parasti. Šogad mēs varam visu sajaukt, jā, visu procedūru. Par to bija jautājums?
Nē, tieši par to, kā viņš rakstiski vai mutiski, vai kā mēs viņu vispār lietam.
To mēs runāsim individuāli ar katru grupu.
Skaidrs.
Jā, kad mums būs konsultācija, Yeah. So I have forgotten to say, so the date and time of the exam and the date and time of the consultation. And typically the consultation is delivered 1 day before the exam. It isn't the reason to have the consultation 2-3 days before the exam, because you are not prepared for the consultation. And the consultation means I don't tell you anything from the lectures. I'll go to answer your specific questions. Means you are already prepared for the exam and something isn't clear to you, and you are already asking to me some specific questions. Don't ask to me to repeat the questions. It isn't a lesson, but it is a consultation. Tas ir vienīgais, ja? Un tad at the consultation we discuss what is the form of the exam. It is written or it is oral, so there are different conditions and different restrictions for these forms. So just now I can tell you very briefly that the written exam is going by following the scheme. You have the question, each of them has, if each of you has the individual specific question, 40 minutes to write. I can't definitely check if you use or don't use some means, but so in 40 minutes you must give me your results, and some 1-2 days I'm checking and saying what is your mark. However, there are disadvantages because if you go, for instance, copy paste from internet and you don't have the knowledge, I definitely see that this is just a copy paste. It isn't your own vision, but very important to have the own vision. If I see that you don't have the own vision, or the own vision isn't clear or isn't right, I don't have a possibility to ask you about some specificity of your vision, because I think that the students are very clever, and somebody can be much more clever than the teacher, and this very clever student has a specific vision that the teacher doesn't know and can't understand. So that is why at the written form of the exam, you don't have a possibility to prove your position, your vision. And this is a very strong disadvantage. You don't have negotiations. At the oral form, we have time to negotiate, not so much, just 5 minutes. But in this case, you have again the question, again 40 minutes. And exactly at the 41st minute, you must come to me and to deliver the answer, to explain the answer, and to explain during 4-5 minutes, not longer. If it is longer and you are not finished, I interrupt you, and this means that the exam isn't passed. So 5 minutes means that you have very well knowledge. You are able to select the information that you need for the exam, for the answer. You are able to analyze this information, and you are able to deliver it very precisely. So after these 5 minutes, I'll ask you maybe 1-2 questions just to verify if it is really from your brain, or is it from the internet copy paste. So, and that's all. And I'm saying you what is the mark. You can say me, yes, I agree, or no, I disagree. You go to ask, what do you prefer, the higher or lower? You can say, yeah, I prefer lower. For instance, 1-2 points, 3 points, this is up to you. Or now I want to have the higher. If you want the higher one, I give you the option, so asking one more question, and so you must reply. If you don't reply, we are staying, we are keeping the marks that that I said to you, that I'm saying to you, offering to you. So this is very briefly about the exam. And so we decide individually with each group what is the form of the exam. For the written form, I don't need the consensus of the group, but for the oral form, definitely I need the consensus. If somebody is against, we go to pass with using the written form against the oral form. Is this clear?
Jā.
Tad, so, jums ir laiks? Ja vajag izskaidrot vēl latviski, jau viss bija skaidrs? Lo?
Jā, viskaidrs.
Jā. Ok. Tad jums ir laiks, diezgan daudz laika pārdomāt, kā kārtot. Jā, nu man īstenībā vairāk patīk mutiski, un es domāju, ka studentiem arī, nu, 61. kursa studenti, viņam vēl nav pieredzes, jā, lielas pieredzes kārtot, bet jūs jau kārtojat vienu sesiju, un, protams, jums bija uztraukums pirms katra eksāminā ar to sirds pulss palielinājās, asinsspiediens palielinājās, tur staigājat koridorus, ja sēdējāt pie datorā, un domājat, ko tad viņš man vēl jautās, un kad es tikšu pie pasniedzēja, jā. A šeit viss ir skaidrs, jā, tad 40 minūtes plus 5 minūtes un atzīmē. 45 minūtes tikai uztraukums. Nav tas stundas, jā, kas parasti notiek, ja gatavojam citu veidu eksāmenu. Tā, kādi jautājumi varbūt, ne? Halo? Halo?
Man ir jautājums. Tur tad sanāk, ka mēs 40 minūtes rakstam atbildi, un pēc tam vēl mums 5 minūtes vajag kaut ko teikt, vai tas jūs teicāt par divām dažādām veidām?
Vēlreiz lūdzu?
Nu, eksāmenis būs, ja raktiski, tad 40 minūtes mēs rakstam atbildi un sūtam jūs, ja mutiski, tad 5 minūtes mēs atbildējam un viss.
Jā. Nu, 40 minūtes jūs gatavojat. Tas jums ir laiks gatavot.
Sapratu.
Bet atbildes garums ir tikai 5 minūtes. Nu, kur tur stiept laiku? Ja zini, tad zini. Ja nezini, tad nezini.
Ja raktiski, tad neko nevajag jums mutiski atbildēt. Vai...
Neko nevajag, jā, bet nu tālāk sapratu, nav nekādas diskusijas, jā. Ja es jūtīšu, ka tas ir norakstīts kaut kur, es rakstīšu divnieku, un jūs neko nevarēsiet man pēc tam iebilst.
Jā, sapratu. Paldies.
Jā, lūdzu vēl. Nav jautājumu. Tā, mēs par daudz ilgi runājam par tām lietām, jā. Palika par 5 minūtes tikai. Okay, we'll start. So, the receptor of the light. So, they are located here at the retinal layer. These are the cells. So, this is the scheme of this retinal layer. The light beam passes the lenses and goes through the eye, internal area. So this is the spherical surface of the eye. And so the light passes, it's a very strange design, passes the nerve layer. So this is the layer of the nerves and excites these cells. You see, typically what is the engineering solution? First excite the cells, and after that the cells gives the signal to the nerve layer that is located, it must be located behind the cells. So I don't know really why the nature has such a solution. So first the nerve layer, and after that and behind it the cells that are the sensors to the light. So we have two kinds of the cells, so-called the rod and the cone. And they are named just because of the shape. The rod really like the rod one, and the cone very similar to the cone. So this layer is aimed to prevent scattering of the light. For instance, the light goes here, may be reflected back and again back. So to avoid this layer prevent reflection of the light that comes back. So this is a good solution, really. So these are the cells that we'll go to speak about them. So what is the reason of two kinds of cells? Have a look. This is a white-black picture, no colors. And this is a colored picture of the same object. So, and really, we can observe, and following our experience, we have several conditions of illuminations of the object. For instance, if the illumination is very weak, we are not able to see the colors. For instance, in the twilight conditions, the colors are not so bright, and even we can't see the colors, we see just the object. So this means that we have the cells that are able to see the object, and they are not able to recognize the colors. However, there are the cells that are able to see the colors. So this is the reason that we have two kinds of the cells. The black one, the white-black image, is delivered by the rod cells, and the colored one by the cone cells. So this is a rod cells design, and this is a cone cell design. And the cone cells are able to detect only three colors: the red, the green, and the blue. How to get the yellow, how to get the brown. So this is the other story, and we continue next time after tomorrow. Please, the questions today.
Jā, tā nav. Tad līdz pirmdienai mums tie datumi ir jānoskaidro.
Piekamies pirmdien, jā. Okay, so all the best. Yes.
Jā, paldies, visu labu.